Naji, thank you very much, and Denis as well for the presentation and this discussion. Our next speaker is Anand Prakash. He will talk about the APP4MC RaceCar, a practical ADAS demonstrator for evaluating and verifying timing behavior. Anand is working as a research associate at Dortmund University of Applied Sciences and Arts. Before joining the university, Anand worked as a software engineer in the display and smart card industry, where he worked extensively in software simulation, debugger, and application security. His research interests include security and safety of real-time applications. Anand, the floor is yours.
Thank you, Marco. Okay. Hello, everyone, and welcome to this presentation on APP4MC RaceCar, a practical ADAS demonstrator for evaluating and verifying the timing behavior. My name is Anand, and I'm currently a master's student at University of Applied Sciences, Dortmund. And this paper is also co-authored by Lukas, Krawczyk, and Carsten Wolff. So coming to the agenda of this, Coming to the agenda of this presentation. So we start with the introduction, where we talk about the current challenges we are facing in the ADAS, modern ADAS applications, followed by the motivation and an example of a RC car demonstrator. This is followed by the APP4MC RaceCar, a model-based demonstrator. And we discuss about the system architecture of the APP4MC RaceCar and the application stack. We discuss about the event chain task model, which we use in our ADAS application, followed by the timing analysis based on the tracing framework. And then we conclude our presentation with conclusion and the future outlook. So starting with the introduction, with automotive OEMs gradually moving towards higher levels of driving automation, the complexity of ADAS applications is increasing. And therefore, the complexity of the ADAS applications with respect to the computation demands is also increasing, since the inclusion of multiple sensors have increased the computational demands, which has led to the introduction of heterogeneous platforms with varying operating frequencies. The ADAS applications are safety critical in nature and must follow hard real-time constraints. This has led to the challenges in analyzing the system's timing behavior, such as determining the end-to-end response time of high-level functionalities, as well as the real-time applications latency. A typical ADAS application consists of multiple tasks with different computational requirements. An efficient mapping of tasks to the processing cores with optimum scheduling policies can further reduce the overall latency of these applications, and therefore a feasible deployment is required. So a feasible deployment of these tasks are required on the processing cores. So, an ADAS application has typically 3 high-level tasks, which is sense, control, and actuate. So each of these high-level tasks are having subtasks which are working in tandem for the proper functioning of an ADAS application. So each task has are scheduled based on the fixed priority or scheduling policies, and they also make use of either a distributed shared memory or a shared memory architecture to interact with each other, since all these tasks are running on multiple cores. And therefore, this leads to the timing analysis of each of these tasks, as the latencies calculations and the end-to-end response time of each of the tasks on a particular core becomes of utmost importance if we need to calculate the overall timing response of an ADAS application. So here we have an example of an existing RaceCar platform, which is provided by the MIT RaceCar. And you can see that there are multiple state-of-the-art sensors involved in it. For example, the ZED stereo camera and the Hokkyu range LiDAR, and the processing element which is used for this particular RaceCar demonstrator is a NVIDIA Jetson TX2 board. However, these existing RaceCar platforms either lacks to fulfill the computational requirements of a complex ADAS application, or is it not developed with a model-based approach. The timing analysis of these ADAS application does not consider the real-life scenarios, and therefore they are mostly done on an emulation or a simulation environment. Therefore, this is where the APP4MC RaceCar demonstrator comes into picture, which is based on a model-based design, and we make use of the tracing framework to generate system trace in real time, which can be used to precisely derive the timing matrix for evaluation. So coming to the APP4MC RaceCar, a model-based ADAS demonstrator. So the system is designed based on the OCM model, which is the operator controller module. This architecture module is one of the proven methodologies to design a self-optimizing system in a changing real-life environment. So here we have a cognitive loop which does all the processing of the real-time processing of the optimization loop, and the next level of the OCM model is the reflective operator, which does the information processing. And the last or the lowest level of the operator controller module is the controller operator, which actually controls the actuators which are used to drive a system or to control a system. So the APP4MC RaceCar is based on the OCM model. The APP4MC RaceCar consists of heterogeneous architecture. By saying heterogeneous architecture, it consists of multi-core and many-core architectures. For example, it uses the components which we will see later, which consist of operating the processing units operating at different frequencies. And in terms of the real-time capabilities, the APP4MC RaceCar, the software stack is designed over the RT Linux, which provides the real-time capability to the applications. And also the GB RTOS is also used in our application. The ADAS application, the overall ADAS application is coarsely based on the Waters Challenge 2019's model, which was a challenge provided by the ECRTS conference. And the system trace generation in real time is generated in real time using the BTF tracing framework, which is also integrated with the ADAS application. So this is the overall system architecture of the APP4MC RaceCar. So the sensors which we are using right now are the ZED2 camera and the RP LiDAR. And the actuators are the DC motor and the servo motor to control the motion of the RaceCar demonstrator. The cognitive loop comprises of the NVIDIA Jetson AGX board, and the reflective operator comprises of the BeagleBone AI, followed by the controller, which is based on the VESC, which is the electronic speed controller. The application stack is derived on top of the RT Linux. So the AGX is enabled with RT Linux, and the high computational algorithms are making use of the GPUs and the tensor cores to optimize the algorithm to reduce the latency of this application. The Jetson AGX and the BeagleBone AI are connected over a CAN interface. So the transfer of or the transmission and receiving of the data happens over the CAN interface, and the BeagleBone AI is also using the RT Linux framework, and the application layer is developed on top of the RT Linux. The VESC is using the Chibi OS RT framework, and the brushless DC motor application sits on top of the GBOS HAL layer, and the communication within the BeagleBone AI and the VESC is done over the UART interface. So this is the overall application stack of the APP4MC RaceCar. The ADAS architecture abstraction is provided is coarsely based on the Waters Challenge 2019's model. So we have a localization task, and which takes the LiDAR input and creates the localization or the mapping of the vehicle with respect to the operating environment. The data is of the localization task is fed to the planner task, and the detection task does the object recognition and detection detection task, which is solely run on the GPU. The SMM task, also known as the structure from motion task, calculates the depth of an object, and this is done by taking the inputs from the camera, as well as the lane detection task checks for the lane detection boundaries, and that is fed to the planner task. Apart from that, the CAN polling task keeps on polling the reflecting of operator to get the vehicle status, which is also fed to the planner task. So now the planner task is having all the information which is required to plan the next move for the vehicle, and based on these parameters, it derives the next vehicle motion parameters, which is fed to the CAN controller task, and from there the vehicle motion is controlled. Now, coming to the timing analysis, how we can ensure that this framework or this demonstrator can be used for the timing analysis of a ADAS application. So the trace generation is happens on the AGX or based on which platform it is working. So for example, if the tracing is generated on the AGX, so it does the timing analysis of the cognitive part. If the tracing is happening on the BeagleBone AI, the analysis is done for that particular component. So with this, we can ensure that we have a model-based or the timing analysis is done in a much more modular way. So here, the BTF tracing framework is integrated to the ADAS applications, and when the ADAS application is executed on the platform, it generates the BTF trace file. And once the BTF trace file is generated, we can visualize the BTF trace file by using a standard trace visualization tool such as the Eclipse Trace Compass. And also we can use the BTF trace file to derive the timing performance matrix, such as the Amalthea trace database, from which we can derive the end-to-end latencies or the response time of each task. And through that, we can do the timing analysis, the overall timing analysis of the ADAS application. So now to conclude, so now we have an ADAS demonstrator with state-of-the-art sensing capabilities. We have enabled or enhanced the computing capabilities of the ADAS application by using high-end GPUs. It also provides real-time capability by using the RT Linux framework as well as the GBOS RTOS framework. And it enables runtime analysis of the real life scenario by generating the traces at real time, which can be further used to derive the timing matrix for analyzing the timing behavior. The future work includes the actual implementation of the BTF trace framework followed by the deriving the timing matrix for evaluating the timing behavior. And also it can be used for benchmarking the image processing as well as the computer vision algorithms which are used in the ADAS applications. So yeah, this concludes the talk for this particular presentation. So yeah, thank you for listening to this presentation, and I'm open to any questions.
Thanks a lot, Anand, for this presentation. Do we have any questions in the audience? Please go ahead.
Thank you very much. I have a question here. Can you hear me?
Yes, I can hear you.
Okay, so first of all, thank you very much. It was a lovely talk. I'm learning more things. My first question is more in relation to your, when you said enable runtime analysis in real life scenario, could you please let me know or let us know what kind of real life scenarios did you take into account?
Okay, so for example, right now, most of the applications which are being, the timing analysis is basically implement or the timing analysis is right now based on the simulation environment or emulation environment. So with this particular RaceCar demonstrator, so once the platform or the RaceCar is moving, so we will trace the tasks in real time when the car is moving, and based on that we will generate the trace in real time, and then this real-time tracing trace file which is generated is used further to check the to derive the timing matrix, such as the deadline miss or the end-to-end latency of a task, or for example the response time of an application, and then that can be used for to do the timing analysis. And based on that, if there is a requirement that we need to further improve the model, overall model of the system, then that can be also used for that, from that perspective. So when I say in real life scenario, it means that we generate the trace when the car is moving and we have this real-time environment available, instead of doing it in an emulation or a simulation environment. Does it answer the question?
Yeah, that's fine. I have another question regarding yes, failed operational states. By any chance, are you taking into account, for instance, if one of the tasks is taking or one of the ECUs get off, the task needs to be moved on to another ECU? It's just a question. Are you taking into account something like this?
Right now, we are assigning the tasks specifically to particular course. So yeah, if a task fails, we are not considering to put those tasks to another ECU or another core, for example. But that's a very good feedback. We will take that into consideration. But yeah, obviously, the task can be further broken down into multiple subtasks, and then based on the scheduling and the priorities that can be offloaded to other ECUs or other processing cores.
Yeah, because it's when you say safety critical, because it's ADAS and we are talking about autonomous and we are talking about safety, the passengers. So the critical functionality should be always available. So I think that's one
Yeah,
point.
so when I say it's a safety critical, it's more from the timing perspective. So it's more about analyzing the timing matrix of an ADAS application, so that there is no deadline miss or there is no delay or increase in the latency of the overall application.
Okay, that's perfectly fine. But I would love to know more about your
yeah
work.
Okay.
It's very nice. Thank you very much for answering the question. Thank you.
There's time for one last question from the chat, which is from Sergey asking, did you collect traces with hardware debugger or on what level?
So right now we are planning to have a software trace. We are not planning to have a hardware trace right now. So the tracing framework will be implemented and it will be integrated with the ADAS applications, and it will be mostly based on the software tracing framework. But we will be also using some of the profiling tools, such as the NVIDIA profiling tool for profiling the CUDA course.
All right. Thank you very much. If there are further questions, I see there's one more in the chat, but we are a bit behind schedule, so maybe you can get in touch with Anand directly.